Okay, so let me show you a demo for Edmond Scarp or Ford-Fulkerson method using BFS as the as the means to find the augmenting path. So for this graph, what we will do is we will run BFS to find our augmenting paths. Okay, so let's see. Okay, maybe I'll choose yellow. Okay, so let's start from um, node S, right? Then from S, S can go to either A or B or C, right? Because of these edges, right? S to A, S to B, S to C. And then from A can go to just D, right? And then B can go to either A or D. And then C can go to only E, right? And then next, let's expand it more. From D, you can go to 3 nodes. You can go to C, E, or T, right? Because we have this 3, C, E, and T. And now, we have found our destination vertex, which is T. So this is the first path that we will try. Okay, so let me encircle this one. SADT. So this is the first path. So for SADT, okay, let me remove these markings first. So that would be here. From S to A to D, and then D to T. So how much flow can you send along this path? So we can actually send 2, right? Because that's the maximum. So 2 out of 2, 2 out of 2, and then 2 out of 3. Okay. So after that, we will continue looking for other augmenting paths. Okay. So we'll continue. From A, you can still go to D, right? Then from D, you can go to 3 places, C, E, and T. And then now you have found SBDT. But for SBDT, if you pass by this one, you actually can't. So SB is possible, B to D is possible, but D to T is not possible anymore because this is already full. So although we found a path here, it's not possible to pass by this path. So SBDT is not possible. So let me write down the first path that we had, which was SADT of size 2, right? So let's continue. From E, you can go to T, and we've found T again. So let's try this one, SCET. Okay, so SCET. So this path here is right here, SCCEET. Now how much flow can we send along this one? We can send 4, right? So 4 out of 4, 4 out of 5, and then 4 out of 5, right? Okay, so we can still continue because this one is not yet full, although SC is already full, so there's no point in expanding this anymore, right? And even SB is still free, right? So let's continue finding augmenting paths. So our second path was SCET with cost of 4. So after that, we'll go to the next level. From C, we can go to E again, and from E, we can go to T again. But again, the problem here is that the AD part of the path is already fully saturated, right? Because AD is already full. 2 out of 2 na siya. So, although we reach T, this is not an augmenting path. Um, After that, we'll expand D here. So, SBD, from D you can go to either C, E, or T, right? So, since we reach T again, let's check. But the problem here again is that DT is already full, right? So this is also not feasible. Now for here, for this one, SBDCET, C will be expanded to E. And then E will be expanded to T. Now we have found another T here. So let's check. SBDET. So it's this one, right? SBDET. This path. So that would be here SB, BD, DE, and ET. And you are still allowed to send one flow here, right? 1 out of 3, 1 out of 1, 1 out of 1, and then you can still add 1 here, so this becomes 5 out of 5. Right? So now our last edge is, or last path is SBDET with size 1. And I say this is the last because all of the incoming edges to T is already full. So there's no way to send more flow through these edges. So this is 2 out of 2. It's already 5 out of 5. So we can send more. So this is when we stop. Okay? So that is the demo for Edmonds-Sharp algorithm or implementation of Ford-Fulkerson using BFS to find augmenting path. Okay? So this was the details. No? So the first path that we saw was SADT, maximum flow of 2. So we add 2 along those paths, and then the remaining capacity would be adjusted. And then the second one was SCET, maximum flow of 4. So we also adjust the remaining capacity. And then the last one is SBDET with flow of 1. So we also adjusted the remaining capacity. And then these are the flows at each edge, right? So the total flow size is 7 because that's 2 plus 4 plus 1. So total flow size of 7. Okay. Now let's see one more example. This time for this graph, and we'll use Edmonds-Sharp again, or BFS, to find the augmenting path for the maximum flow. Okay. So in the BFS, we'll start with S. Okay. Maybe I'll redo this one so that I'll start at the very top. So we start at S, and then S could be expanded to A, C, and E, right? Just either A, could be C, or it could be E. Now from A, you can get to either B, C, or D, right? B, C, or D. Then from C, you can get to D or E, right? And then from E, you can only get to F, right? Now, from B, you can go to either D or T. Now, we have found T, so let's check this path here. So, let's check this path, SABT. So, for SABT, where is that? It's here. SA AB PT. Okay. Now, how much flow can we send along this path. We can send maximum of 9, right? Because this is the bottleneck here, 9, A to B. So if it's 9, then this will have 9 out of 10, 9 out of 9, and 9 out of 10, right? Okay, so let's go to the next one. Try to expand C. So from C, you can still go to D or E, right? And then from D, you can go to F or T. So this is just BFS, right? You're just expanding the nodes based on their neighbors. But since we've found another T here, which is the sync vertex, then let's check let's check this one. So SA D T. Okay, so it's in here, SADT. So if it's SADT, where is that? That would be here. SAAD DT. So along this path, how much can you send? You can actually only send one, right? Because this one only, SA only has a remaining capacity of 1 because it's already 9 out of 10. So if we send 1 here, then this becomes 10 out of 10. This becomes 1 out of 5, 1 out of 15, and then 1 out of 10, right? So you'll also notice that SA, the branch SA is already full, right? So we could actually ignore the branch SA already because we know that even if we find a path from S to T, we can't pass through SA because this edge is already full. Okay, it's already fully saturated. So we can ignore the other nodes here. We don't need to expand those anymore because we know that SA is already full. So let's focus on the next part, which is the SC and the SE parts. Okay, so let's go back to yellow. So from D, you can get to F or T. And then we found another T here. So let me use another color. Okay, so SC DT. Right, so this is our third path that we found. SCDT. SCDT here. So SCDT. How much can we send along that path? So that is this one, SCCDDT. So we can actually only send amount of 5, right? So 5 here, 5 here, and then since this will be added by 5, this will become 6. So 1 plus 5 is 6, right? So we added 5 along SCDT. And then after that, okay, we'll expand E here. So from E, you can go to F, right? By the way, we'll also notice that from S to C, it's already full. So we don't also need to expand these parts here anymore because we know that even if we find a T here somewhere, right, it won't be passable because of the SC. SC is already full, 5 out of 5. So we'll just focus now on the SE part, SEF. Okay, so let's continue with F. So from F, you can go to two places, either C or T, right? So from F, you can go to C or T, and now you've found another T. So let's check if we can pass by that. So okay, maybe 200. Like first one better. Okay, maybe we'll use orange here. So SEFT is our fourth augmenting path, right? So SEFT. Now how much can we send here? And that is actually really open. So SEFT. So we can actually send 10 along this path because the bottleneck is this one, F to T. Sorry. Yeah, so that's 10 out of 10. Okay. Now, can we still send more? So there is still an open slot here, 10 out of 15. So we can still send up to 5. And then there's still 9 out of 10 here. So there is still a chance that we could find an augmenting path. So let's continue. So from C, you can go to either D na lang, right? We can't go back to E because it's already part of the path, right? Because if you go back to E, then obviously you're just doing a loop. Okay, so from D, where can you go? You can either go to F or T, but since F is already visited along this path, we can go directly to T. Okay, so that is the next na path that we'll use. Maybe I will use okay, maybe red, then something like this, maybe. It's not visible, so let's just use red. Okay, so SEFCDT is our last path. Okay, so that's SEFCDT. So how much can we send along that path? So where is that path? It's here. S to E, E to F, F to C, it's still a forward path, C to D, D to T. So it's all forward paths. So how much can we send here? We can actually only send 3 because the C to D is the bottleneck, 5 out of 8. So the remaining capacity is only 3, right? So we'll update this. We'll make this, that was once 10, right? So if we add 3, this will become 13. Then this one will become 13 as well. Along this one, it will be 3 out of 6. Then this one will be 8 out of 8. And then this one will be from 6. So this becomes 9 out of 10. Okay? So now, this is already the final set of augmenting paths, because even if you expand the rest, you can't find any more. Okay? So we have SABT, SADT, SCDT, SEFT, SEFCDT. So what is the total size of the flow? So the total flow size is how much? Total flow is equal to, so this is 10 plus 15, 25 plus 3, that's 28. Okay, and let's check. So this one you have plus 10 plus 5 plus 13. So from S going out, it's 28. And then from T going in, you have 9 plus 9 plus 10. So that's 18 plus 10. So going in is also 28. Okay, so that is our example for this graph using the Ford-Fulkerson method, specifically the Edmonds-Karp algorithm. Okay, so these were the paths that we found, and that was the flow size. Okay, so that is the demo for maximum flow. So let's say this is our graph. Okay, this already has a flow, right? So let's see how much is the maximum flow here. The max flow, we can compute that just by looking at the flow going out of S or going into T. So from S you get flow of 10 plus 5 plus 13. So this is actually 28. And that's the same for T, right? You get 8 plus 10 plus 10. That's here, 8, 10, and 10. And then for S, that's 10, 5, and 13. This is also 28. So the max flow size is 28. So we'll expect the min cut also to be 28. Now, how do we find out the min cut? So we will start at S. Okay. So S is here. So S is discoverable. And then we will try to search or try to find out which nodes are reachable. Now, can S go to A? S to A is already full, so we cannot pass by this edge. Okay? Same with S to C, because S to C is already full, so we can pass by here as well. Now, S to E is passable because there is still remaining capacity here of 2, so E is reachable this time. Now, from E, which nodes can we go to? We can go to F because E to F still has remaining capacity, right? So there's still remaining 3. So F is also reachable now. From F, can you go to T? Well, you can't because it's blocked off by the 10 over 10 na flow. F can go to C because there's still remaining flow of 3 here, right? 3 out of 6. So C is also reachable this time. Now from C, can you still go to D? Well, you can't because it's blocked off by 8 over 8. Can you go to A? Well, you also can't because you can't do a backward flow here because it's already empty. So 0 out of 4, right? So you can't do a backwards flow. Same with F to D. You can't do a backwards flow here, so because it's empty, so it's not passable. So we are actually stuck at C. We can't do go further. So this would be our partition. So the reachable nodes that are reachable from S are S, E, F, and C. And those that are not reachable are, so this is one group, S, E, F, C. Okay? And then the not reachable non-reachable nodes are A, B, D, and T. So that is this group. Okay? So now this is already our cut. So the min cut is the two partitions S, E, F, C and A, B, D, T. Okay? So that is the minimum cut. And if we just clear this out and do it again, so if it's S, C, E, T here, S, C, E, F, and then A, D, B, T here, what would be our min cut capacity? So which edges go from A going to B? So let's see. So that would be this edge, right? From S to A. So SA has a capacity of 10, and then AC is not part of it because it's going backwards. We have CD, which goes from C to D, so it also crosses to the other subset. So CD is 8. DF is not part of the edges because it's going backwards. And then finally we have FT, just going from F to T, subset A to subset B, right? So FT, capacity of 10. So this is also 28. So the min cut capacity was also 28. Remember, our max flow capacity was also 28, right? Because of the 10 plus 5 plus 13 here. So they were the same. Okay? So that's it. Max flow 28. Reachable from S is the 4 nodes. And then this is your min cut. And then the min cut edges would be used to compute the capacity, which is also 28. So this is the final cut for this flow.